Hi folks, so this is the lecture in lieu of actually having been in class. So um, if you guys get this lecture, I think this will help you do the lab next Tuesday night. I'm going to go over a lot of this again next week, so um, pay attention in here, but be aware that you'll be able to ask questions next week. So this is a lecture, or this material this week is on a thing called medium scale integration. So just write that up here, medium scale integration, integrated parts. Okay, so these are chips that have some higher level function than just gates. So they're more than just but they're less than microcontrollers or something like that. They have a specific applications. Okay, and we're going to go over them. So some of those medium scale devices that we're going to go over are listed here in this list here: basic adders, parallel adders, comparators, decoders, and so on. And what I'll try to do is illustrate the function of each of these, and then hopefully that'll help you next week when you do lab. You'll be showing how these things work, but you'll actually be using the Quartus board to do these. Okay, so let's start with a basic adder. So an adder is a chip, and what it does is has 3 inputs and 2 outputs. And in this case, there's an A and a B input where you add the binary number. So it's a 1-bit adder. And if there's a carry in, you would add that as well. So it's a, if you're adding something, typically you're adding 2 numbers. So maybe A plus B, and then also the carry in. Okay, so these can be 0 or 1, all of them. So depending on what the sum is, will dictate the sum out and the carry out. So for example, if A was 0 and B was 1, I added those and there was a 0 carry in, the sum would be 1. So this would be the sum. And there's the carry out is likewise 0 because there's no carry. If there is a 1 here and a 1 here, then the sum is 0 and the carry out is 1. And if the carry in was 0. So 1 plus 1 is 0. So the other combination would be if I had 3, a carry in, A and B 1, so this would be a 1 and a 1. So it's just binary addition. So that's a full adder. The full adder is indicated by the fact that it has a carry in. Okay, let's go to the next page. The full adder timing diagram is shown here. I did this in previous version of Multisim, but if you have a timing diagram for this thing, for this chip, so this is what you'll, similar to what you might look at it on Quartus, where if you had a if you were simulating the input. So this is my carry, or this might be my A, B, carry in, and then sum, and then carry out. So this is a 0, 0, 0, which means I get a sum of 0, a carry out of 0. Here I've got a 1, a 0, a 0, So I get a sum of 1 and a carry out of 0. Likewise here, no, wait, this is a 0, a 1. I get a carry in of 1. Oops, nope, that's still 0. So I still have a sum of 1 and a carry out of 0. Now I got a 1 here, a 1 here. 1 plus 1 is 0. So the sum is 0 and the carry out is 1. And so on for all of these. So this would be the timing diagram for a full adder. Okay, a half adder has no carry in, but it has a carry out. So this is an implementation of a full adder with half adders. Don't worry too much about that. Here's an example of some full adders, and it asks you to figure out what the okay, so if I have a 1 there, my sum would be a 1. My carry out would be a 0. If I have two 1s here, this would be a sum of 0 and a carry out of 1. This would be identical. Okay. So you'll see these full adders again. This is an implementation of a 2-bit adder. So these previous chips were single bit adders, but let's say you needed to add something a little more complicated. So how do you make a 2-bit adder out of 2 single bit adders? So in this case, you'd have your least significant figure, your least significant binary figures on the right, so A1 and B1. You'd add those, and if your carry in for the first one is always 0, but then that carry out is carried in over here to this sum. Okay? This could go on and on. So now if you wanted a 4-bit adder from single bit adders, you just keep feeding that carry out to the carry in. And a more sophisticated version of that chip would be implemented all together. So again, you take this basic functionality and you pack it into a single chip, and you manufacture that chip, and it can be useful. So this is a 4-bit adder all packed into one chip. It has at least 8, 9, 12. It has at least 14 pins. Okay, so it needs pins for power and ground as well. So inside of here, there may be 50 or 60 gates that achieve this function, and you may not want to wire it up all the time, so they put the functionality back in the chip. And earlier on here, it showed the implementation of the gates that are inside of this single bit adder. So the single bit adder has 1, 2, 3, 4, 5 gates. So a 4-bit adder is going to have 4 gates for each one of these digits. And again, you can expand the 4-bit adder to an 8-bit adder. The 4 bits are added here. The carry out is carried over in here. And then these are the more significant bits, and so on. So you can keep expanding this. So that particular chip is a 74283. So the next chip that we'll look at is a comparator. So this compares two numbers and determines whether they're greater than, less than, or equal to. So this is the functionality of a comparator. So if you have a 2-bit comparator, it's comparing A0, A1, and B0, B1. There's a circuit that will determine whether they're equal or not equal. So it might look something like this. So this is a 4-bit comparator. So if I have a 4-bit 4-digit binary number. It compares A and B. And there's 3 outputs where A can be greater than B, equal, or less than. So if I had the number 0, 1, 0, 1, which is the number, if this is my MSB, that would be the number 10 in base 10. And then I had a 0, 1, 1, 1, which would be the number 14 in base 10. In this particular case, B is greater than A, so this would be a 1, 0, 0. Now if I wanted to make an 8-bit comparator, I'd have to cascade 2 of these together so it would compare the most significant bits first, and it would determine if the most significant bits were high. Then you know that if the most significant bits are high, that the output has to be A is greater than B. So if A's most significant bits are greater than B's most significant bits, then A is greater than B. Likewise, if the most significant bits of B are greater than A, then B is greater than A. It doesn't really matter what the less significant bits do. And if the most significant bits of M and B are equal, then you have to examine the next bits. So if these are my most significant bits, and these are the least significant bits, assume these are equal, let's tie this high, and in this particular case, it will compare these 8 bits, and the output will indicate which of the 8-bit numbers is greater. Okay, we're going to look at decoders, quite a bit of decoders. So decoders do just what they say. They take a particular pattern of inputs and they translate it into a specific output. Okay, so let's look at a couple examples here. This is any particular combinatorial gate is some sort of a decoder. You have a specific input, and the output that comes out is quite specific to whatever your input is. So here's a decoding logic for producing a high output when the input is a 1011. Okay, so that is a particular decoder for this pattern. There's some specific decoder bits that translate, do something, are a little bit more useful. One is the 7442 binary coded decimal to decimal decoder. Let's see if I can blow this up a little bit. So what happens in this particular, let's zoom out. If I have a 7442, I'm going into the inputs with a number. It's a binary number. It's a 4-bit binary number. And depending on what the value of that 4-bit binary number is, it will activate one of these 10 outputs. So it's binary coded decimal. So if I go into this chip with, for example, a 000, it'll activate the 0th output. If I go in with the number 1, if I go in with the number here, 0, 0, 1, 0, which is a 2, it will activate the second output, and so on. And it will count up. As these count up, as this number counts up, it will successively activate each one of these outputs. So the output here, as I cycle through the inputs going from 0 through 9, so this is a hex number, so these are activating these binary inputs as a 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. So this is going to be and so on. This is just going to count up. And then 4 is 0, 1, 0, 0, and so on. So it's activating those inputs, and then successfully, this is an active low output. So when it activates that output, it drops it low. And if you look at this output in a little more detail, you can see there's a circle at the output, and that indicates that it's an active low output, meaning when it's activated it goes low. So that's what's going on in this diagram. So this particular chip, because it only counts to 9, it's considered a binary coded decimal decoder. So it decodes the binary value here into its BCD equivalent at the output. So again, a lot of this analysis is based on using timing diagrams to figure out what the inputs and the outputs are. So what are the values, the inputs and outputs of A and B? So we've done this a few times, but this is a 0, this is a 0, this is a 1, this is a 0, and so on. So it's going to be important for you guys to be able to read these timing diagrams. Maybe not second nature, but it certainly should be familiar how to translate from code back into the timing diagram. Okay, there's another chip. It's the 7447. And what it does is it translates a binary coded input. So again, there's 4 bits. To represent all the decimal numbers, I need to have at least 4 bits. I need to be able to count to 9. And depending on the value, the binary value going into the input, it will activate a 7-segment display, and it'll display that number. So in this particular case, it's activating a 1001, which is the numerical value, the binary coded decimal value for 9, and it's turning on these LEDs in a 7-segment display in a specific pattern so that the 9 is activated. So let me just go over here and explain that a little bit. How a 7-segment display works. So you have in a 7-segment display, you have 7 LEDs. Okay, so this is my 7-segment display. So this would be the top LED, this would be my side, and so on. So if I turn these on, I can create, like, for instance, a 3 if I turn these on and leave these 2 off. And the nomenclature that's used is, this is A, and this is G. So these are the 7 segments. So A through G. So this is going to selectively turn on. If you look at this, these outputs are labeled A through G. So it's going to turn on those segments depending on what the input is. So this particular decoder is specifically used for 7-segment displays, the 74LS47, and I believe you're going to see that in lab. Okay, the first decoder that we talked about was a binary coded decimal decoder. This one is a 16-bit decoder, so it can count up to more than just 9. It can count up to 16, so it has 16 outputs. So if I put in, for example, a 1, 1, 1 here, it will activate the 15th output. If I put in all zeros here, it'll activate the 0th output. So if I count up here at my input, I successfully activate those outputs. So here's my inputs, here are my outputs. So for example, if I do a cross section right through here, this is the number 0, 1, 0, 0, that's the number 2, and I'm getting the output 2 activated. So this is the counting up, these are the outputs. That particular chip is a 74, I don't know what it is, 16-bit decoder. Sorry, 4-bit decoder. Okay, a lot of these medium scale integration chips have other pins that have strange names, and they never seem to be the same from one set of documentation to the next. In this particular case, is called an enable pin. And these enable pins allow you to expand the data range that you can use these chips for. So if you need to have a decoder that's higher than 16, it needs to be able to go up to, say, 32, then you'd need to expand the range of this. And you'd also need to expand the number of inputs, right? Because if you're going up to 32, you need 5 bits going in. So what they use is this enable pin. So this chip will is active low. So when this is low, this is enabled. When A4 is high, this is disabled. So what's happening here is, as I count up, so these are my lower order out. So for example, if I had a 0, 0, 1, 0, and then my other input here, so I'm going in with the number 4, base 10, then it's going, this chip is activated, this chip is inverted, so this one, I'm actually going in with a 1 here. So this is disabled. This isn't working. And therefore this 1 that translates over to here does not do anything. It doesn't activate the 4th pin down. Whereas it does activate the 4th pin down here. So for this particular one, it would activate, this would be a 1. Or this would be a low. And the rest of these would be high, since this is an active low output. If I went in here now with the number say, now that's 1010, that's the number 20, base 10. Now it's not going to activate this one. It's going to activate this one. Now is a 1. This is a 0. So this is the chip that functions now. And this one is off. So this one has no effect on this output anymore. And instead, it's going to go to this one. This is going to be activated. The rest of these are going to be 1. Okay, so you use these enable bits to expand the range. Okay, an encoder sounds similar. It works in reverse. So instead of taking the, like for instance, a binary coded input and converting it to a decimal output, it's the other way around. So this particular chip is a BCD encoder. So depending on which of my inputs is low, it will generate that binary coded decimal output. And it only counts, like if, for instance, this is an active high, this is the truth table, so all the empties are low. So if this is high, these are all low. So if this is a 1 here, so in this particular case I had a 1 here, and these were all low. Then I'm going to activate none of these. These are all going to be 0. Now as this goes to a 1 here, now I get a 2, or sorry, this will be a 1, and then so on. So if I had, for example, a 0 here, 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 and then this was a 1, and then these are all zeros, this would activate the number 5. So that would be a 1, this would be a 0, 1, 0, 1, or the number 5 at my output. Now a lot of times these particular chips, the only one that matters is the most significant bit. So I could have a 1 here, and I could have a 1 here, and a 1 here, and a 1 here, and 1 here. The only one it cares about is the most significant one. So the output would be the same. It would be this output. So that is a priority encoder, meaning it's only going to count the most significant bit. Okay, so that's what it was saying here. HPRI means highest priority only. So here's the truth table for a 74, 148, or 147. So it's a binary coded decimal to a decimal to binary decoder. And again, it has some input pins that I need to check out from the truth table from my spec sheet that indicate what pin is being, how to make this thing work like a priority encoder. So I need to have my GS pin low, wherever that one is. It's not labeled on there. And my E0 pulled high. If I have them both high, it's basically turned off. And if I have one of them high and one of them low, I basically pull them all high. So if I want it to work as an encoder, I need it to be in this range here. Sorry, a decoder. So I need to have, sorry, this is my enable input. This has to be low, and when it's like that, it works as advertised. Okay, so one of the last things we'll talk about are multiplexers. So a multiplexer these are cool devices. They will have a select pins, and the select pins will determine which of the inputs go to the output. So for example, if I select 0, 1, that's this pin, that's the input number 2. This, whatever data appears here, will go to my output. If I select the number 1 here, 0, 1, then the data that appears at D1 will go out. So for example, if I have this input and I have some, say, clock signal coming through here, that's what's going to appear at Y1. Okay? So here's an example of my select pins. I'm selecting pin 0, pin 1, pin 2, pin 3, and then so on. So whatever appears at those inputs, that's what's going to appear at the Y output. So in this particular case, I'm selecting 0. So whatever is here comes to the output. Now I'm selecting 1, so what is ever here, now this is a high value, is going to appear here. 2, and so on. So 3 now, it's this output, and then if I select 0 again, now it happens to be high, and it just keeps going like that. So it's determining what input gets funneled to the output. Another thing I could do is have I could have a static input. Let's erase all this. So in this particular case, I had high, low, 4 lows, 2 highs. So I had 4 lows, high, 4 lows, 2 highs. So this would be a tied high. Then these 4 are tied low. And then these 2 are tied high. And then this one is tied low. Okay, that's what I had here. So I had a static input. And now as I select that input, so it's counting up here. In this particular case, S, the selects, are counting up. So it's 0, 1, 2, 3, and so on. It selects 0. I get a high output. So I select 0. So this high output appears here. And then 1. Now this output appears here. 4 lows. And then I select 5, 1, 0, 1. So 5 is high, and 6 is high. So it's just counting up. And then 7, 1, 1, 1 is low. So 1, 1, 1. That's the 7. So that's how that's working. And then there are different configurations for multiplexers. In this particular case, I have 2 select pins, and then there are effectively 2, or 4 in this case, 4 dual input multiplexers. So depending on which number I select at the data select is going to determine which of these outputs goes to one. So if I select channel 1A, I'm also selecting 2A and 3 and so on. So they all do the same thing depending on which of the 2 that I'm selecting. So this can either be a 0 or a 1. Just a different configuration for a multiplex. Here's an example of using one of those multiplexers with the 7448 decoder that we talked about earlier. And in this particular case, it's selecting one of these 2 digits to go on. So if I select this to be a 0, if this is a 0, that means I'm selecting A0 to go out to A, and A1 to go here, and so on for these 4 multiplexers. So I've selected a 0, therefore I've selected this, this, and this to go to the output. But at the same time that I've done that, I've chosen this particular decoder is one thing I didn't mention with respect to these these 7-segment displays is the way they work. You have diodes in there, and if I select, for example, if this is segment B, this has to get grounded. So if I select B, I'm applying power to B, but in order for the LED to go on, I need to complete the ground path for it. And this particular pin is providing the ground path, so it's allowing all of these segments to go on. If this is open, none of these segments can illuminate. If this is closed, then I can operate it in the way that I expect. So what I'm doing here, by putting a 0 in, I'm selecting the least significant digit to go on. And if I were to put a 1 in here, it would turn this one off and turn this one on, and it would allow the current to flow through the most significant bits. And so in doing that, I am the outputs here. If I put a 1 in here, the number B0 would be fed through the output, and it would illuminate this digit, and you could have 2 different digits appear here on these 7-segment displays. I know that's a little confusing to understand, but if you actually to build it, I think it would be clear. We're going to build stuff like that in Quartus, because those boards you have allow you to do that. Okay, here's a multiplexer used in that configuration I just mentioned with a static input. I can basically make any kind of combinatorial, at least with 3-bit input, I can make any combinatorial type circuit that I want. Remember, we did all this with gates before, but with a multiplexer, if I made this, for instance, a high, all these inputs high, then this Y output is going to be proportional to this this output. So A0, when is this going to when is this going to be high? It's going to be high when I activate this pin. So this is a sum of products. So in that particular case, A in order to select this pin, this would be a 0, 0, 1. That would be a 0, 0, 1 here. That'll give me a 1 output. Now if I go in here with this one, this is going to give me a 0, 1, 1. It's selecting this output. That's high, and so on. So this is sort of another way to do what we just spent 5 weeks doing. Okay, so this is summarizing again what a multiplexer does. Okay, the last thing we'll talk about is a demultiplexer. And the demultiplexer is just the 138 decoder. So this is a 3-bit decoder used in a particular configuration so that instead of having in this particular case, I've got one input, 3 select pins, and now I have 1, 2, so these are my select. This is my Y input, and these are my outputs. So if I were to select, for example, a 0, 1, 0 here, that's the number 2. That means that output, that input will go to that output. So this is just like a decoder, except for instead of using an input that these are my select pins, CBA, so depending on which one of these select, I get a high output or a low output because it's active low. But if I toggle this between activating the chip and not activating the chip, it will effectively do exactly the same as a demultiplexer. So if I were to put, for example, a signal like this in here, this would come out. And really what I'm doing is I'm using this enable pin G2 in order to, this is effectively my Y, this is going to be my Y input. So what I'm doing is going back and forth between G2 being low, so here it's low, and let's say I picked this input right here. So I picked 0, 1, 0, so it's 0, 1, 0, so I've picked this one. And I'm going high, low, high, low. So I'm going high, low, high, low. So really what I'm doing is going low, high, low, high, low, high. So it in effect, it looks exactly like a demultiplexer. It's just that I'm activating and deactivating the chip by going between here and here. So this high-low transition is the same as this high-low transition. And what it's effectively doing is making this go high, low, high, low. Again, a little confusing, but that's how it works. Okay, that's all I had for this, and I hope it helps you to do the lab next Tuesday night.